Domain 6 is security architecture and design. Looking at the candidate information bulletin, IC Squared tells us that the domain contains the following. The security architecture and design domain contains the concepts, principles, structures, and standards used to design, implement, monitor, and secure operating systems, equipment, network applications, and those controls used to enforce various levels of confidentiality, integrity, and availability. Information security architecture and design covers the practice of applying a comprehensive and rigorous method for describing a current and of future structure and behavior for an organization's security processes, information security systems, personnel, and organizational subunits, so that these practices and processes align within the organization's core goals and strategic direction. The candidate is expected to understand the security models in terms of confidentiality, integrity, and data flow diagrams, the common criteria protection profiles, technical platforms in terms of hardware, firmware, and software, and system security techniques in terms of preventative, detective, and corrective controls. What we'll look at is some technology concepts first. The most important thing here for a common security architecture is an information security management system. We see the ISO 27000 series coming out now, replacing the ISO 17799. ISA is an information security architecture. Also, if you see the word best practices, it is now known as good practices, because your best practices is not my type of best practices. And architecture is a solution which we will take a blueprint or a framework and apply that to get a working solution. Also, we apply this in the infrastructure, such as IT and a business relationship. A trusted computing base is the whole environment which is verifiable and also auditable. Ring protection, this means the granularity or fineness of controls. We'll look at that from ring 0 to ring 3. The kernel is at ring 0 and where everything goes through. It's a full testable and verifiable solution. A reference monitor is a keyword for me, and I always refer to as a traffic director, where everything goes to, and this will actually make up based on the rule set of which subjects, such as a user, also can be an application, has got access to what objects, such as applications, datasets, or any other resource. Objective of an enterprise security architecture includes cohesion between business units, because we talk the same language. We can make strategically aligned business and security decisions. And when you look at these architecture and different models and so on, you'll see that business drives it, and security should be an enabler to ensure that the business is protected adequately from a logical point of view. It can provide security-related guidance, security best practices or good practices. It can define security zones, segmentation of business functions. We can consistently manage IT risks because we've done a proper risk management process. Reduce the overall cost of managing that risk because we actually know what we're doing and it's not an ad hoc reactive process. Better and quicker security-related decisions. We can promote interoperability, integration, and ease of access. We can also provide a frame of reference. Characteristics of a good security architecture is all to do with strategic. Then we look at the business strategy, we look at the security environment and access control, and how the whole design. So it actually looks at the direction the business is going, so that will be adapted to the business. Holistic, where it emphasizes on the importance of the whole, however the independence of the parts. It allows for multiple implementations, and usually what I say is eclectic is the word. Eclectic means that we will take the best from different frameworks and adapt it for our benefit. Now, when we actually have a poor architectural planning, there will be issues like the inability to support new business initiatives, unidentified security vulnerabilities, such as the increased frequency and visible security breaches, poorly understood and coordinated compliance requirements, poor understanding of security goals and objectives. Now, when we look at the design, we need to consider that we have to include people, such as senior management perspective, driving that forwards, financial operations, which is my processes, and then my technical perspective, that's my technology. So it's people, processes, and technology. So the process that we have to look at from a top down approach where businesses looks at the bigger picture. So environmental trends, where we're going to with the business. This is my flexible business processes. Then underneath that, we have our business drivers, such as business and related security needs. Then where IT strategy comes into place, this IT security, which looks at operations, access control, and the management of information. And right at the low level, we'll have the security architecture, which is supported by my policies, my standards, my procedures, and my guidelines. Now, IT security principles are fundamental statements. It defines a philosophy, requirement, or is a formal commitment, and that's usually line management, and it's very challenging to define. Now, one thing I've mentioned before is the establishing of a security zone as segmentation. When you have an architecture, you can design so that my dealer environment is a separate environment from my IT support and also then from other like public domain or guest access in my environment or even normal users. This will allow me to design an architecture and then drive that through from my network design. Also, information classification or this policy is definitely a requirement due to the fact that if I don't have an information classification policy, it means I don't have any security because I don't know where to start and where to spend the money. It also, as we know, that information classification depends on the sensitivity or the age of the information itself. Now, when we actually look at a definition process for my architecture, I need to look at security principles, my architecture principles from a security point of view, and then drive it down to a detailed security architecture and then my technical framework. So if we look at the maturity of a security architecture, we start off by initiating all my stakeholders of the security program. That is my support, my buy-in. Then I will document my strategy, my principles, and my policy. The security organizational structure is really important because this identifies who reports to whom from a business perspective and also line management, who will look after what from a custodian and ownership. I will apply or select a security architecture, a formal architecture framework, and then what we'll do is have enterprise security controls based on this from end to end, and then also a security technical framework. And once we've implemented that, we need to consider if we have to go through either any compliance or certification processes as defined by legislation or regulations. Example is PCI DSS for a banking or financial organization. Then assurance is the auditing process to make sure that what I have designed and implemented is working as designed. And finally, security metrics, if we can measure what we've done, if there's an improvement. And once we have security metrics, we have and take note that we are doing it properly. So this is important to have the measurement at the end of the day. Now, a couple of architecture frameworks we can look at include items like the Zachman framework, which gives us a complete overview of IT business alignment. It is two-dimensional with intent, scope, and principles. And as you can see here, what I would recommend is to look at your own organization, take the two-dimensional approach here, and see if you can apply and look at certain items within your organization. Now, we have seen some management frameworks previously, such as ITIL, COBIT, COSO, and also COCO. Basel, from a financial organization point of view. And then there's another two I'd like to just address. Six Sigma we haven't seen before, and CMMI we did touch on previously. And then right at the outermost perspective is the ISO, the International Standards Organization documentation. And the 17799 has been replaced now by a 27,000 series. Now, when we look at implementing our information security management system, it is a 6-stage process. We have to define an information security policy. We have to define a scope of the information security management system, perform a risk assessment, manage that identified risk, and then we have to select the controls to be implemented and applied, and then prepare a statement of applicability. ITIL, it's published in the UK as British Standard 15,000. It focuses on IT services such as release management, change management, and also the current release version 3 at the moment is focusing also on security management. COBIT is control objectives for IT and related technology, and it emphasis on regulatory compliance, removing compliance from a management perspective, looking at from the outside. COSO is the Committee of Sponsoring Organizations. The emphasis is on the importance of identifying and managing risk. The objective, we've got 4 objectives here, which is strategic. That is our high-level goals aligned with and supporting its mission. We've got operations, such as the effective and efficient use of its resources. Reporting objective, it means the reliability of reporting. Compliance with applicable laws and regulations. Now, Basel 2.3, that's the latest iteration, establishes the basic requirements for risk management in a financial environment. It guarantees the financial stability standards. It's considered the standard practice and is applicable in financial areas such as bank, forex, possibly insurance. Now, Six Sigma is a data-driven approach, and it's used on a measurement-based strategy. There are 2 sub-methodologies, DMAIC and DMADV. Now, DMAIC defines, measures, and analyzes, and then improves and then looks at the control. The second methodology, DMADV, we define, we measure, analyze, and then we design, if there are any requirements, and then verify that design. Now, a little bit more detail, if I can go into that. DMAIC has the following components. We define the problem, the voice of the customer, and the project goals specifically. Then we measure key aspects of the current process and collect relevant data. We analyze the data to investigate and verify cause and effect relationships, determine what the relationships are, and attempt to ensure that all factors have been considered. Seek out root cause of the defect under investigation. Once that's done, we will improve or optimize the current process based upon data analysis using techniques such as the design of experiments, poker yoke or mistake proofing, the standard work to create new and future state process, set up pilot runs to establish process capability. Then control the future state process to ensure that any deviations from the target are corrected before they result in defects. Implement control systems such as statistical process control, production boards, visual workspaces, and continuously monitor the process. The DMADV has the following steps. We will define design goals that are consistent with customer demands and the enterprise strategy. We will measure and identify CTQs, which is the characteristics that are critical to quality, product capabilities, production process capabilities, and risks. Then we'll analyze to develop and design alternatives, create a high-level design and evaluate a design capabilities to select the best design. We will design details, optimize the design, and plan for design verification. This phase may require simulations. Then finally, we verify the design, set up pilot runs, implement the production processes, and hand it over to the process owners. The next is the capability maturity model, integration. We have 5 levels. We've seen it from a software development point of view, where this actually was created to manage a maturity of software development environment. We have initial, unpredictable, ad hoc, and reactive. Level 2 is repeatable, where it's process aligned with projects and it's reactive. Level 3 is the defined process aligned with the organization, and this is proactive. Level 4 is managed. It's process measured and controlled. And finally, at level 5, it's optimizing level, which focuses on continuous business improvement. Then the alignment of framework is TQM, which is total quality management, is about planning. ITIL is about managing the quality. COBIT is about the control points. Six Sigma is about the skills and disciplines. CMM or CMMI is about maturing the process. And the ISO standards are the outermost perspectives. When you look at system level architecture, we need to look at the whole architecture of the hardware and software. We look at hardware, the addressing, memory, some storage, some risk around that. There are software such as machine types and operating states, a system recovery depending if it falls over, and also you've seen in domain 2 the OSI 7-layer model, which is also important. We have the system unit, a motherboard, a computer bus, and the bus is all dependent on how many bits are running at the same time. And currently we're sitting at about a 64-bit bus in most of the desktops. We have a central processing unit, which is the brain of the computer, which contains the arithmetic logic unit, the ALU, and control unit. It does all the fetch and execute. It does have pipelining to ensure that the instructions are running and not interfering with each other. There are special items such as interrupts that can interrupt a process to make sure that, for example, if you press a keyboard, it'll have an interrupt and the application running will be notified of that interrupt and you can take action on that. Processes and threads, and this is important when we look at multitasking and multiprocessing. Multiprocessing means there's multiple processes running at the same time. Multitasking is where some processes are running, but they have each time a slice of the CPU time. So they're not running all at the same time, but they are being switched between tasks, and it looks like they are running as multiple processes. We have complex instruction set computing and reduced instruction computing. When we look at memory, we have random access memory, the normal RAM. We can have cache memory to speed up a system. RAM and ROM. RAM is random access memory, and ROM is read-only memory. So that can only be written to, and it is normally static. So static RAM stays the same, and 10-to-1, it will be there when we switch it off the machine and switch it on again. It will be there. Dynamic RAM, on the other side, it is not volatile, meaning if I switch off the machine and switch it on, it will be gone. Now, memory protection has issues like process isolation, so the processes cannot interfere with each other. Hardware segmentation from a memory point of view and CPU, that will actually separate the RAM from each other in the computer. Virtual memory, that is swapped to disk. And virtual memory is not real memory. This is memory that usually is extended to make it seem like the machine has got more memory. And swapping is a swap space, also to create additional storage capability of some operating systems. Now, firmware, we can have program read-only memory. We can have erasable program read-only memory and extended erasable program memory. Now, program PROM can only be written to once, and that is it. Erasable, we can erase it once or twice, but it does affect the longevity of the firmware. And then the extended can be erased and written to many times. We have a programmable logic device, PLD. So EEPROM and EEPROM is a PLD. Now, also, when we look at hardware, we've seen quickly a review of that. There's some addressing you have to look at, memory and storage. Now, storage can be anything from a hard drive, which is non-volatile memory. You have external USB sticks and anything like this, which is also a storage method. Now, basic security concepts. Before we look at the fundamental models, we need to understand what is the basic security concept for when we design these things. A trusted computing base is all hardware, firmware, software, processes, and also the inter-process communication. It has to be simple and testable. The smaller it is, the more easy it is to test it for adequate protection. Now, a trusted computing base enforces security policy. It monitors 4 basic functions, such as process activation, execution domain switching, that is from user to supervisory mode, memory protection, and all input and output operations. Now, this is a sample of a list of objects requiring protection. However, the list is not exhaustive. As you can see, there's memory files, data sets, programs in memory, directory of files, hardware devices, and there you have your hardware abstraction layer in the operating system, data structures, operating system tables, which are very critical, instructions, there's password files, authentication mechanism, and other protection mechanisms. Now, reference monitor concept is an abstract machine which must be tamper-proof, always invoked, and verifiable. The security kernel, though, checks every access, enforces least privilege. It verifies acceptable usage through authorization concepts. Now, we've seen before there are 2 primary concepts that we have to worry about when we look at the reference monitor. We have subjects and objects. Subjects are users, programs, processes, and logon identifiers. We have objects, which are files, programs, instructions, data, and also even hardware. Now, when we look at protection concepts, we need to consider that we have subjects with a higher trust and subjects with a low trust. So when we look at identifying the authentication and the authorization of those subjects, we need to look at an example where users may have access to confidential data and then also at public domain data. Now, also during the execution state, a user, the application or the process can be in user mode or in system mode. Now, when you look at system mode, there are a couple of words that mean the same: supervisory mode, administrative mode, and kernel mode. Now, the process isolation between these modes, we need to ensure that the object's integrity are intact. It prevents interaction between the processes. There's independent states, as we've seen previously from a user or a supervisory state. And then process isolation methods includes encapsulation of objects, time multiplexing of shared resources, so that's slicing, naming distinction, and virtual mapping. When we look at ring protection, there are 4 rings that we have to consider. Ring 0 is the kernel, which is system mode. Everything has to run in supervisory or kernel mode. Ring 1 is the input and output, such as device drivers. Ring 2 is my utilities, such as system utilities. And ring 3 is user applications running in user mode. Now, virtual machines mimic the architecture of actual systems and is provided by a operating system. It is used for running legacy systems, but the risk may include a theft of VM copy, skill requirement, and however, we need to consider the advantages whereby we can actually have DRP processes very up and running very quickly with virtual machine. Looking at the operating system protection, it can include the following: user identification and authentication. We've seen discretionary and mandatory control, access control in domain 1. We need to worry about the complete mediation, which means possible multiple paths to the data, and we have to protect each one of those. Object reuse protection, such as memory leakage or data remnants. Memory leakage is a programming error usually whereby memory is assigned but not freed adequately, and this memory will go into a limbo stage, which can never be used and addressed anymore. And a system sometimes would what they require a sanity check to reboot it and make sure that all those memories are recovered. Data remnants is when we don't clean an area used before and the information stays at that memory and it can be accessed by other applications to use it at a later stage. Now, operating system protection also can include things like audit, and then we need to consider clipping levels. Clipping levels are a certain level where exceptions are noted. For example, if a password is incorrect, that's fine. However, it's 3 times incorrect, we have a clipping level, and that users normally look locked out. Audit log reduction means that if a message is coming through the operating system 1,000 times, the same message, it should say to you, this message was received in the last hour 1,000 times, and not give you 1,000 messages. Trusted path is a path that we can trust from access to the endpoint, and then also intrusion detection and intrusion prevention can also be used for operating system protection. When we look at establishing a confidence in trusted systems, there are certain ways of measuring this. We have an evaluation criteria. Examples include the American-based Rainbow series, and I'll take 2 out of there. There's the Orange Book, which defines the Trusted Computer System Evaluation Criteria, TCSEC, or the Trusted Network Interpretation, the TNI, or the Red Book. And all these are part of the Rainbow series, which contain a lot of colored books depending on what you want to look at. For example, the Brown Book is the Trusted Facilities. That is American-based. Then we have European-based, which is the Information Technology Security Evaluation Criteria, or ITSEC. And then finally, an international standard known as the Common Criteria, which is an ISO standard 15408. In your information pack, there is a lot of documentation looking at version 3 of the Common Criteria. Now, when we look at the Common Criteria, there are issues that it addresses. Some methodologies, alignment between the American and the European one. There's a common structure when we look at a evaluation. also a common base for the evaluation of different systems. And there's an international arrangement called, this is a certification based on the Common Criteria Recognition Agreement, the CCRA. And what I've done with this table is right in the middle, we've got the Orange Book, or the United States TC-SEC. And I've identified all those areas, such as the minimal from D right up to verified design. Now I've got common criteria on the left-hand side and the European one on the right-hand side. There's basically a relationship between these levels, however, not one to one, but it gives you a fairly good indication. Now, when we look at certification and accreditation, certification means there are security modes of operations, specific users and their ratings, applications and data sensitivity will be considered, the system and facility configuration and location, and also interconnection with other systems. That is certification. When we look at accreditation, this is an official management decision to operate a system at the security mode for a stated period and is a formal acceptance of risk within the operating system. Now, once we've gone through that, I think the final one here is a lot of theory, and you will get questions about this, is some of the fundamental security models. Now, when we look at the security models, there are two components or two areas that we look at from these. One is confidentiality and one is integrity. And when I say to the guys, any model with I in the name seems to me like being integrity, and if it's not an I in the name, it's confidentiality. For example, one of the two models you have to know is the Bella-Padula confidentiality model. This is a hierarchical state machine model with three fundamental models, such as read-only, write-only, and read-write. It has a secure state. Only if the policy allows us, access will be allowed. And we define access rules whereby we can access of subjects to objects. Now, this is important to look at the star property. We have the simple security property rule, where it says that read is based on own access and lower level and not at a high level. No read up. We have the star property, which I can write at my own level, write secret data to a high level without compromise, and cannot write secret data to a lower level, no write down. And then finally, the strong star property, which means read-write only at your own level. You need to consider here any action, such as if you read up or write down, confidentiality will be affected negatively. Now, BIBA is the first integrity model which addresses our integrity. It's also based on a hierarchical lattice. It has elements. It addresses the first goal on integrity. Mathematical dual of confidentiality, which means access tuples. We've got subjects and objects, and prevents unauthorized modifications and corruption. Now, if we look at the star property here, the simple integrity property means that we can read at our level of accuracy, read at a higher level but not lower. Possible corruption, no read down. This integrity of the star property, we can write at our own level and write at a lower level, and cannot write at a higher level, no write up. Once again here you can see if we don't go through a cleansing or a decontamination process, we will affect integrity negatively. And then invocation property means in BIBA that it restricts the ability to request a service or execute a process residing at a high integrity. Now, if we compare the two, the Bella-Padula is confidentiality, BIBA's integrity. Both are information flow models, as they're considered a flow between different levels. Simple means reading, star means writing, and now just remember the direction. Then also there's another model we can quickly look at, which is the Clark-Wilson integrity model, where we have users as active agents. We have transformation procedures, TPs, which is programmed abstract operations such as read, write, and modify. We have constrained data items, known as CDIs, which can only be manipulated by the transformation procedures, the TPs. We have unconstrained data items, UDIs, and then also integrity verification procedures, IVPs, which checks the consistency of that constrained data items, or the CDIs, externally. Now, the Clark-Wilson integrity model addresses all three integrity goals, which means it prevents unauthorized users making modifications. It prevents users making unauthorized modifications, and also maintaining external and internal consistencies, defines well-formed transactions, and a separation of duties. This access control matrix defines users, which is my objects on the left-hand side, and then my subjects on the top. As you can see, file 1 to file 3, and also dataset 1 to dataset 3. Now, it gives you the capability here of reading, writing of these files by the users. So this is an access control matrix. Now, the information flow model means that each object and subject is assigned a security class and value. The information is constrained to flow in the directions that are permitted by the security policy. And this, to me, is a source of separation of duties, the SOD. Now, the Brio-Nash model is also known as the Chinese wall security model, which cannot have access to two clients at the same time. For example, front office, back office, or if you're consultant, you cannot log onto your client's network and your network at the office at the same time. It has been designed to prevent conflicts of interest and also based on the information flow model. Now, in the book that you've been given, on those pages, there are the models that you actually can go through, such as the non-interference, lattice, state machine model, the Graham-Denning model, which is the right of subject on specific objects, which is also known as the Graham-Denning 8 rules, and also finally the Harrison-Russell-Ullman model on page 385, which means the access rights of subjects and the integrity of those rights. This completes domain 6, and once again, I believe about 10% of the exam.